Well, greetings from beautiful northern Michigan. We've had our first snowfall, and Fuck It Word has put out a new video on what I like to refer to as silly perspective. So let's have a look and see what he has to say about this subject, and then let's see if we can sort out the truth. Okay, so here's the shot that's got Nick's nose in a knot. This is from a video by Mr. Miles Davis. Of a shot of a bridge with mountains in the background. He says that the shot was taken from a height of approximately 210 meters, that the bridge towers themselves are approximately 210 meters high, and the mountains in the background are between 415 and 500 meters high. The distance to the bridge is 45 kilometers, and the distance to the mountain is 90 kilometers. Okay, so first and foremost, should we be able to see the entire bridge from a vantage point of 210 meters? So we pull out our handy Earth curve calculator. We put in our eye height of 210 meters and our distance to the object of 45 meters, and we find that the horizon from that height should be more than 51 kilometers, and we certainly should be able to see the bridge from its top down to the water. So far we check out. Now, while overall this is a really good video, I would like to point out a couple of problems that we could easily fix. First of all, it would be very simple to get a Google Map location of his camera site so that we could find the actual elevation from where he took this picture. Second, we could also get the name of the bridge and be able to actually measure for ourselves the distance from his observation point to the bridge and confirm that it is indeed 210 meters high. However, taking him at his word, and assuming that he is somewhere in the vicinity of this bridge and the bridge itself is 210 meters high and it is 45 kilometers away, according to the curve calculator, we should easily be able to see the base of the bridge, and indeed we can. Now let's go ahead and pay some attention to the mountains in the background of this picture. They're reported to be 90 kilometers away, and in height on the right at 415 meters and on the left at 500 meters. Now, from an observation height of 210 meters at 90 kilometers, we should have approximately 115 meters of those mountains obscured by the curve of the Earth. Okay, so having a look at this in light of what we saw in the curve calculator, we do appear to have a observation elevation of somewhere in the vicinity of the top of those bridge towers, and the mountains are clearly below the bridge towers. We should be able to see both the bridge and the mountains. Now the serious problem, of course, is not that we can see both the bridge and the mountains, it's the fact that the mountains themselves appear to be below the level of the bridge. That's completely incompatible with the concept of a flat Earth, where we're just looking straight out and lining it up like a gun sight. Okay, let's examine why this is a fatal problem for the flat Earth model. Let's assume that we have a flat Earth, that our observation height is 210 meters and the top of the tower is 210 meters. As you can see, our line of sight directly over the top of the tower is parallel to the flat Earth. Even if we start at an observation height of 0 meters, look to the top of the tower is 210 meters off the ground, 45 kilometers away, we will still have a significant amount of hill visible above the top level of the tower. In this photograph, we clearly don't have that. Okay, so here we have the raw photograph. It's not zoomed, and nicely the peaks with their height and distance from the observer are clearly listed. Now the claim has been made that the observation height of this photograph was actually considerably lower than was reported, and the differences in the size of the hills versus the bridge's perspective. In reality, given the fact that less hill is exposed than one would expect from even with the Earth curve calculator, I suspect the observation height of this photograph is actually higher than 210 meters. Again, it would be very nice to have the exact location listed with its elevation in addition to that photograph. But let's see why perspective really doesn't have anything to do with this apparent difference in height. Now, here's just a simple drawing. We've got a nice flat horizon, we've got a sun, and then we've got a spot on the horizon where the sun is going to set. And what we want to do is we want to show the sun going from its current position to that vanishing point or point of convergence on perspective. Let's see what would happen with that. Now, we've all seen this convergence diagram before. This describes how things appear to get smaller and approach a vanishing or a convergence point in the far distance. This is a way to artistically represent a three-dimensional object in two dimensions. Let's see how that actually works with our sun diagram. Okay, so here's where we start using real perspective instead of silly flat earth pseudo perspective. In real perspective, you draw a line directly from the top and the bottom of the object to the vanishing point, and all representations of that object as it travels towards the vanishing point fit within that cone right there. And it's the entire object, not a part of the object. And it starts off large on the left side of the picture here, the top left, and then as it goes down to the vanishing point, it literally disappears. Notice that as it stays within the cone, it's the entire object getting smaller and appearing to go further away. At no time does one part of the object disappear while the other part remains. So for example, if you look at the sun, you will see a round glowing disk. As perspective were to bring that down, the sun would become smaller, smaller, and smaller, and then it would disappear to a point. At no time would the sun remain the same size at the vanishing point that it does at the upper left, and simply half the sun disappearing or three-quarters of the sun disappearing, etc. It will progressively get smaller until it disappears in its entirety. Now first let's get an example from the curve of the Earth. Here we have three ships. The one on the left is just a hair over the horizon, the one in the center is between us and the horizon, and the one on the right is well over the horizon. Notice that on the near ship in the middle, we can see the entire ship. Then we start to lose some of the water line on the ship on the left, and on the right, which is well over the horizon, we've already lost the entire hull of the ship and we can only see the superstructure. That is due to the obstruction of the bulge of the Earth between us and that ship on the right. Now contrast that to perspective changes. Notice here as a spherical bowling ball goes down a smooth bowling alley, we can see the entire bowling ball. It just gets smaller all the way to the pins. We don't lose any of the bottom of the bowling ball. And on this close-up you can clearly see that the ball is only touching the bowling lane at one point, and you can see space underneath it. It is definitely not sinking in to the horizon or the bowling alley due to some sort of silly flat earth perspective. Now Nick attempted to conduct an experiment to show how this could be done due to perspective alone using these lighters. Let's go over his method. Now here is how he attempted to prove that. First he lined up 4 lighters of equal height along a level table, and on the last one he elevated the lighter with a book. However, in his efforts to try and somehow make the 500-meter mountains in the background appear to be lower than a 210-meter bridge tower on a flat Earth, he now postulates that the elevation of the observer is much lower than 210 meters. Now, according to Flat Earth Silly Perspective, that means the mountains clearly would come below the top of the towers due to reasons, I guess. But let's have a look and see what that actually looks like in the real world on a flat Earth. Okay, so here's our line of sight diagram from earlier in the video. Notice that this is to scale vertically, and it's to scale horizontally, although the scales are different. We have a 210 meter observation post on the left and a 210 meter bridge tower in the middle. Looking straight across, we should see 210 meters up on the mountain, which is 500 meters high. If we look from 0 meters above our 210 meter tower on the bridge, we should still see some of the mountain above us. In order for the mountain to appear below the bridge tower from our point of view, we actually have to have a line of sight similar to that dotted line, which, as you can easily tell, goes below ground surface. But that's okay. Nick has an answer for that too. Okay, so as we said, the line of sight has to start actually below ground level. So here's the little hole that Nick dug himself into, trying to explain the obvious with silly flat earth perspective. So Nick, fuck it word, once again, thank you for at least making an effort on this. I'm glad to see that you are attempting to make some experiments. However, I'm going to give you a little bit of advice. First of all, you cannot start every experiment and every video talking about how we all know the Earth is flat. You don't design experiments with a conclusion determined in advance and then see if you can shoehorn the data into it. This silly perspective nonsense that you keep doing is not real perspective. Ask somebody what real perspective is. Understand that sometimes your observations will not match your predetermined conclusion. And simply because those hills are below the tower on the bridge does not necessarily mean that you have to come up with some sort of reason to try and explain that other than the fact the Earth is a sphere. So you keep trying, and I'll keep watching. Thanks.